Hello dear students, I'm Meghamala, and today topic I'm going to talk about is operation in active mode. So in the previous class we have discussed about different types of modes of operation of BJT, and moreover basically we have discussed about what is bipolar junction, and previous to that we have discussed about what is a microelectronics. So as we are discussing, or else as we are pondering on the microelectronics subject, the very first and foremost topic in that is bipolar junction transistor, and we have discussed about what is a bipolar junction transistor, and what are the different modes of operations that it takes place. So, and now in the today's topic we will discuss about the operation in active mode. So how the bipolar junction transistor, as I said that it acts in different modes, right? So in different modes of operation it takes place. So in this scenario, in this particular area, in active mode, how the bipolar junction transistor is going to be operated in this particular active mode. So before the very first slide talks about the transistor, it operates in three different modes: saturation, cutoff, and active modes. So unlike resistors, which enforce relationship between voltage and current, transistors are non-linear devices. So we know that active devices and passive devices, right? So this particular statement says that the voltage and currents, okay, the relationship between the voltage and current are with respect to the voltage and current. Voltage and current can be we can assume, or else we can consider the voltages and current with respect to linear and non-linear circuits, right? But whereas the transistors are non-linear devices, where here in the transistors we are concentrating more on the current and as well as the voltages. So here in the previous class we have discussed what is BJT, and how many types of the transistor BJT can have, the like NPN transistor and PNP transistor. So NPN transistor is nothing but the P-type transistor, where it's all about the relationship between, or else it all about the transmission of the holes and as well as the electrons. So in NPN transistor, most probably rather than considering the PNP transistor, we will go for NPN transistor. So here, as I said, you like with the resistors, unlike resistors, a linear relationship between currents and voltages can be seen with respect to the non-linear devices like the transistors. So here we will discuss, as I said, now we will be discussing three different modes of operation in the using BJT. So BJT can operate in active mode, BJT can operate in saturation mode, and also BJT can operate in the active mode. So when you compare these three modes of operation, I say that the mode of operation, the active mode of operation is quite different when you compare these two, when it is compared with the cutoff and as well as the saturation region. So first one we will see, we will keenly understand the operation of BJT in three different modes. So first one will go with the cutoff mode. So what is this cutoff mode says that? So in this cutoff mode, so if you observe here, this is the NPN transistor in cutoff mode. So here in this NPN transistor, there are two junctions can be formed. Okay, so one is emitter base junction and another one is collector base junction. So emitter base junction and collector base junction, the current flowing the current and the voltages. The current and the voltages can be observed, or else the current can be flown through this junctions. So here both junctions are reverse bias. So in emitter base junction and collector base junction, we see that the operation of a transistor in this cutoff mode, we say that the junctions are in reverse bias. Okay, the junctions are in reverse bias. So no current flows. So as it is in the transistor is in the reverse bias state, so we see that there is no current flows. That means the current becomes 0, I is equals to 0. So since it is acting in a reverse bias condition, so we say that there is a nil current flows in the between the junctions, that is emitter base junction and also the collector base junction. And the transistor is, so obviously when the current is 0, that means when nil current is flowing through the junctions, we say that it is the transistor is in off mode. So the transistor is in off mode because the current flowing through the junction is 0. Then so when the current is 0, so we are saying that the transistor is in off mode condition. And so the transistor is in off mode condition, it means that it is an open switch. So we all know about what is a closed switch and open switch. There's a difference, right? There's a difference between closed and as well as the open switch. So here we are saying that the transistor is in open switch condition when the current flowing is 0. When the current flowing is 0, it means that the current flowing I is equals to 0. It says that both the junctions, that means what, emitter base and the collector base, in both the junctions they are in the reverse bias condition. And this mode is used for switch off applications. So as this transistor, the transistor BJT can act as off state in cutoff mode. Okay, in cutoff mode, BJT transistor, it acts as an off state. Why? Because here the current flow is nil. The current flow is 0. Where the current flow is 0, it means that the voltage flow is also obviously 0. So here you see junction 1 and junction 2. So junction 2 is collector base junction and junction 1 is emitter base junction, right? So here it is a VBE voltage source, that is this is a one section and this is another section. So the voltage flowing across the base and the collector is nothing but VBC, and the voltage flowing across the emitter and base is nothing but VBE. Right? So, but one thing you have to remember that in cutoff mode, the current flow is nil. So that's the reason we are saying that the BJT, it acts the BJT acts in an off mode state. It acts as a open switch in cutoff mode. Then coming to the second mode of operation, that is saturation mode. So in this saturation mode, as we have discussed here, the EB junction, emitter base junction, and the collector base junction, the emitter base junction and the collector base junction, we say that both junctions are forward bias. So here both junctions are in a forward bias, saying that the current flow through the device, so the current flows through the device. So as they are in the forward bias, it means that there is some current flow. Okay, we see some current is flowing across these junctions and the transistor is in on mode. So we see that when the current is 0, then it says that no current is flowing, so it acts as a switch off state, right? Switch off. And the condition, in which mode it is a switch off, it is in cutoff mode. Whereas here some current is flowing in between the junctions, so we are saying that the transistor is in on state, right? So it is in on state and acts like closed switch. So this mode is used for switch on applications. Why it is in switch on applications? Because some current is flowing across the junctions. So what are those junctions? With respect to emitter base junction and also with the collector base junction, they both are in forward biased. So if both are in reverse bias, then we can say that there is a nil current flowing through it, and so the transistor acts in a switch off state. Whereas here in saturation mode, some little current is flowing through the junctions, between the junctions. So we can say that as these are in a forward bias condition and some current is flowing across them, then we can say that this BJT, the transistor, is in on state, right? So this is a same junction 1 and junction 2. Junction 1 is emitter base, junction 2 is collector base. And here VB is a voltage across the base emitter and the base, and VBC is a voltage across the base and the collector. So this is a small figure states about the NPN transistor in saturation mode. Okay, so far we have discussed how the transistor acts in saturation mode, and also in the cutoff mode. And now we will see how the transistor acts in a active mode. So here in this active mode, you have to remember that in this mode, one junction, that is emitter based junction, is in forward bias, whereas collector based junction is in reverse bias. So that this is what the more important point to be remembered when you are discriminating the current flow, or else when you are saying the difference between the different modes of operation, the BJT, and with respect to different modes of operation, you have to remember that in active mode of operation, one junction will be in forward bias and the other junction will be in the reverse bias. So when it is in the forward bias, we say that some current is flowing across the junction. When it is in the reverse bias, we say that nil current is flowing across the junction. But in this active mode, in this particular scenario, we can say that a little current, some current is flowing. A little current is flowing across one junction and no current is flowing in the another junction. So this mode is used for the amplification of current. So in cutoff mode condition, we say that it acts as a switch off state, right? So different applications that we can consider this cutoff mode, the BJT in cutoff mode is switch off conditions, switch off applications. Whereas in saturation mode, we say that the switch is in on state. So for switch on applications, we can consider this saturation mode of operation. And now this active mode, in the active mode, we can say that the amplification of current. So with respect to the applications which are comes under the amplification of current, we can directly consider the BJT in the active mode. So here, junction 1, junction 2, we say that, for example, junction 1 is for reverse bias, or else we can consider that the junction 2 may be forward bias. So overall, we have understand that there are three types of modes of operation we have discussed so far. One is cutoff mode, second one is saturation mode, and the third one is active mode. So in the cutoff mode, we have two junctions, right? Emitter base and collector base, right? So in the cutoff mode, we say that both are in reverse bias. When both are in reverse bias, we understand that the nil current is flowing through them. And in saturation, we say that the both are in forward bias. So in the forward bias, we say that some nil current is flowing through it, right? And then now in active mode, we are saying that among these two, junctions, one is emitter base. Emitter base junction is forward bias and the collector base junction is reverse bias. So here we are saying that this particular thing help us to amplify the circuit. Okay, amplify the current. Okay, in current amplification circuits, we can go with directly the transistor mode of operation in active region. And now, as we are discussing about the operation in active mode, this is our current topic for the day, operation in active mode. We will see different we will even more understand how what are the difference, or else what are the changes that we can see when the transistor is acting, or else when the transistor is operating in the active mode. So here we have two figures. So particular figure 1 says that different regions of BJT transistor. So this is an NPN transistor. I said that the BJT can have the NPN transistor and as well as the PNP transistor, right? So this is the NPN transistor. You have to know the difference between NPN transistor and the PNP transistor. So in NPN transistor, you can see the arrow mark towards the emitter, whereas in PNP transistor, you see the arrow mark towards the base, or else towards the base, right? So this is the NPN transistor where the current flowing, we know that this is a collector, this is a base, this is the emitter and terminal and the base. So this is emitter, collector and base. So the transistor has three terminals: emitter, collector and base. So here you see we have the current which is flowing in the base is nothing but the IB, base current, and the current which is flowing in the collector is IC, and the current which is flowing through the emitter is IE. Okay, representations of current is IC, IE and IB, right? And then we will see we have RC, RB and RC and RB. RC and RB are nothing but the resistors with respect to the terminal. So here two resistors we have considered. We have two resistors as RC that with respect to the collector terminal. RC is resistor, collector resistor, and RB is the base resistor. And we have the junctions. So as I said, two junctions can be formed, that is emitter base and as well as the base and collector. So here the voltages at collector and base, voltages at collector and base is considered to be VBC, and the voltage at collector and emitter is considered as VCE, and the voltage at base and the emitter is called as like VBE, right? And then we have the basic two resistors, two voltage sources, that is VCC and VBB. So this is the different regions of BJT transistor. This is how we can indicate the current and the voltages with respect to the three terminals, right, in the BJT transistor. And now we will see how the current flow in active mode. So I said that the current can be amplified. The amplification of current can be seen when the transistor is acting in the active mode region, right? So here, if you observe, the current flowing through the collector is IC, and the current flowing through the base is IB, and see, this is VBE, the base with respect to base and VBE, base and emitter, and it is VCE, emitter, and voltage, VCE voltage. So here you can see that beta DC and IB. So we say that the amplification of current seen over here. So this is a beta DC. Okay, beta is nothing but the amplification factor. Okay, current amplification factor is called as beta, and DC is a current source, and IB is the current which is flowing through the base, right? So as I said when the BJT is when the transistor is operating in an active mode, we say that the amplification of current is observed. So what is this amplification of current is this beta into IB. What is beta? Beta is nothing but it's a constant. So it's the amplification factor, right? Current amplification factor, whereas IB is a current which is flowing in the base. So in the external bias voltage VBB, that is forward bias, is the base emitter junction. So in the base emitter junction, this is base, emitter and collector. So in VBE, so the base emitter junction, this is the base and emitter, right? So in this particular junction, we see that VBB is a forward bias, right? So the source. So this is a VBB source, and here this is a VCC, right? So this is a VBB and this is a VCC. The current flowing, see, always when you are drawing some figures, remember that indication of currents and voltages is must. It's very important. So the current flowing through the collector is IC, current flowing through the emitter is IE, and the current flowing through the base is IB. And here it is VC is a voltage source, and here VB is a voltage across base and emitter, and VCB is a voltage across collector and base. And now from this figure we are saying that the forward bias, the external biasing voltage is VBB. This is a VBB, external biasing voltage, and here it is VCC with respect to the current collector. So when it is forward bias, so we are discussing in active mode, we are saying that in active mode, one junction would be in a forward bias and the other junction would be in a reverse bias. So which junctions are in forward bias? Emitter base junction R is in forward bias, and reverse bias is in collector and base junctions are in the reverse bias. So this is what the active mode talks about. So when it is in forward bias, so which is in forward bias? EB, emitter and base, will have a voltage drop across it similar to diode. So we can say that from this particular sentence, we can say that BJT can also act as a switch, and also when you compare it with the diode, we say that there is a voltage drop. Okay, there is a voltage drop with respect to base and color emitter. In base and emitter, we see that there is a voltage drop, right? So approximately 0.7 volts or higher. So at this particular VBB, we see that there is a voltage drop. That voltage drop would be around 0.7 volts, or it may be higher, right? But to simplify things, we are considering it as 0.7 volts in the current and the voltage designated as VBE. So that means what? This particular junction here. So this is in this particular area we are talking about. So this would be 0.7 volts, or it may be higher. So VBA is approximately is equals to 0.7 volts, and by using the Kirchhoff's voltage law, okay, Kirchhoff's current line voltage law, these are the basic things in electronics and device circuits. So by using this Kirchhoff's voltage law, okay, Kirchhoff's voltage law, the current across RB, that is base resistance, the voltage across base resistance is VRB is equals to VBB minus VBE. So this is VBB and this is VBE. So the total, what do we say? The total RB, VRB, right? The base resistance, the base voltage. So the total base voltage is nothing but it is a difference of VBB and VBE. And not only using Kirchhoff's voltage law, but also by using Ohm's law. We know that Ohm's law is equals to V is equals to IR. V proportional to R, right? So V is equals to IR. I is a current, R is a resistor, and V is a voltage. So by using this Ohm's law, the voltage across RB, okay, the voltage across RB is nothing but the base resistance. The voltage across RB is given as VRB is equals to IBRB. So we know that VRB, V is equals to IR. V is equals to IR as per the Ohm's law. So IRB, IB and RB, which is equals to VBB minus VRB, right? So simply what we are doing by using Ohm's law, okay? By using Ohm's law, V is equals to IR, IB and RB, which is equals to VBB minus VBE. And now after rearranging this the above equation, we get the equation in the DC base current, okay? We get the equation in terms of current. So we know that current I is equals to V is equals to IR, right? So I is nothing but voltage with respect to resistance. So IB, which is equals to VBB minus VBE by RB, right? So this current we got it from the above expression, and this above expression we are writing by using Ohm's law, okay? And previously, that means what? In active mode, transistor acts in the active mode. We are writing the expressions by considering Kirchhoff's voltage law and also Ohm's law. So by using Kirchhoff's voltage law, we can get the voltage at the collector with respect to the emitter, which is equals to VCC. So till now we have discussed about VBB, right? VBB. So what is this VBB minus VBE, which is equals to VRB. This is what we have discussed so far. And now in this particular slide, we will discuss about the applying Kirchhoff's voltage law at another junction. This junction is emitter base junction. In the emitter base junction, this is what we have observed. Whereas in collector base junction, CB junction, in collector base junction, what we are saying is the same method follows. That is, firstly considering the Kirchhoff's voltage law, VCE, which is equal to VCC minus ICRC, and IC is equals to beta into DC IB, right? And then VC is equals to VCC minus, in place of IC, simply substituting IC in place of ICRC. Now, to get the voltage across the collector base junction, and now we are talking about the get the voltage across collector base junction, right? So what we are doing is we need to subtract the voltage at the collector and the voltage across the base. So these two, that is collector, we need to differentiate, or else we need to discriminate both collector and base, right? So VC and VBE. So here VCB is nothing but VCE minus VBE. VCE is equals to VCE minus VBE. So the voltage across collector and emitter is nothing but it is a difference between VCE and VBE. So if the collector is at a lower voltage than the base, then the collector base junction will be forward bias. So what let's ponder on this last sentence again. If the collector is at a lower voltage, for example, VC is equals to low than the base, right? So that is VC is low and then base, then the collector base junction will be forward bias. So if this is lower than this, then obviously what happens is VCB, collector base junction, okay, CB junction is in a forward bias. So this is about the active mode operation of BJT. So in the active mode operation of BJT, we are describing two things. Okay, one thing is we are saying that when the transistor is acting in a active mode, when the transistor is operating in active mode, we are saying that it goes with forward bias in one junction, that is emitter base junction, and it is going as reverse bias in another junction, that is collector base junction. So the voltages across the base emitter and the voltages across the collector emitter is this. The difference between VBB and VBE is nothing but VRB, and the voltage across VCE minus VBE is nothing but the this VCE, right? So one is forward bias and this would be reverse biased. So this is the BJT region of operation. So here if you observe, this is a graph talks about IC and VCE, right? Collector current and the VCE, voltage across collector and as well as the emitter. And this is about the different IB, different base currents. So we see that, as I said, is 0.7 volts on higher. Okay, in the active mode, we say that the voltages can go 0.7 and beyond it. So this is a region, we call it as active region. This is the active region, right? This is nothing but this is a saturation region. Okay, and here it is a cutoff region. So this case, there should be no current that flow through the collector. So why there is no current is flowing through the collector? Because EB junction, EB junction is forward bias. Some current flows through it, and CE junction is reverse bias. So this collector, we say that there is no current flow. The current flow is nil. However, in reality, if you observe, there will be a small collector current leakage that will flow due to thermally produced carriers. So we might say that there's no current flow. But when it comes to the existence, in reality, we will observe that a little current will flow. Okay, little current will flow in the collector base. So since the collector and that particular little current which is flowing in the collector is nothing but the collector leakage current, and that collector leakage current is very small. Okay, it's very small and we can neglect. We will obviously neglect. Why? Because it is in a reverse bias condition. In reality wise, if you observe, we say that a little leakage of current is flowing in the collector current. But when you're considering practical, we say that can be omitted. Okay, that will not comes into consideration. So VC is equals to approximately equals to VCC. The voltage across collector and emitter is approximately equals to the source current, source voltage. Okay, collector source voltage, that is VCC. So this IB is equals to IB current is 0, and RC IC is equals to 0. Here in this particular, the no current, the current flowing is 0, and you call this as a little current. As I said you, in reality we see that little leakage of current can be flown, that we are representing with respect to ICE naught. VC is equals to VCC. Okay, so this is the BJT regions of operation. And now coming to the saturation region. In this saturation region, the BJT operates the saturation when its collector current is not dependent on the base current. The collector current is not dependent on the base current and has reached a maximum. So here the collector current is reached a maximum where it is not dependent on the base current. The condition for this is to happen that both the base emitter and the base collector junction should be forward. So here in this saturation region, we are saying that emitter base and the collector base, base emitter EB and base collector R should be in the forward bias. Okay, so this case what happens is VB is equals to approximately 0.7 volts and more than higher, and VC is equals to 0. So 0 current flows in the current and emitter junction, that is VCE is 0. Obviously when there is no current, the voltage source, is also becomes 0, whereas in VBE, base and emitter voltage, we see that there is a the voltage across the junction base and emitter is 0.7 volts, right? 7 volts. So this is a small diagram pertaining to this saturation mode, and this already we have discussed in the previous slide. And now we will see how the current and the voltage flow in the saturation mode. So the current, if the collector is in low voltage, then the bias. Okay, if the collector is low voltage, then the bias, that means VC is less than VB. Then CB junction, that is collector base junction would be in the forward bias. So this is a small difference that you have to remember in saturation mode with respect to the voltages. So since VB is since CB, the collector base junction is in a forward bias, says that the voltage VB is equals to, it becomes 0.7 or higher. The same thing we have observed when the transistor acting in a active mode region, right? So in the active mode region also we have observed that the collector base junction, it could go for 0.7 voltage or 0.7 voltage or higher. The same thing happens here in with respect to the saturation mode. We say that the collector base junction is in a forward bias, since the voltage is VB is equal to 0.7 volts or higher, and then VC becomes 0. The current voltage, the collector voltage, the voltage across the collector terminal, it becomes 0, drops to 0 volts, and such that when the current is 0, it means that no current flows in the collector region. And then what happens is, because it says that the collector base junction would be in a forward bias. So here, as there is an increase in the base current, as there is an increase in the base current by increasing the VBB. As you are increasing the base current, obviously there would be an increase in the base voltage, that is base voltage source VBB. In this case, what happens is the collector currents also becomes increases. Okay, as IB increases, collector current also increases. When both current, that is base and collector currents, when base and collector currents are increases, what happens is VCE decreases. Obviously VCE decreases, that means the voltage drops across RC also increases. The resistor across the collector increases, but there's a drop down voltage across the collector and the emitter, that is VCE becomes it reduces. And then as we further increase, so one thing remember, as you are increasing the base current, you are increasing the source base voltage, that is VBB, and also you are increasing as you are increasing the collector current, it seems that the collector resistance also increasing, but what happens is there is a slight breakdown voltage occurs at VCE. And then as we further increase IB, IC also increases until where VCE is saturation. Until VCE saturation, when you are still increasing current, base current, we see that there is a still increase in the current, collector current. So when these two currents are increasing at these two terminals particularly, then we see that there is a saturation level. The voltage can reach up to a saturation called VCE saturation. VCE saturation, and this is the active region. So here by using this is load line analysis, right? So here in this load line analysis, we are talking about the quiescent points also. We'll come across a quiescent point. We will discuss about this quiescent point in the coming classes. So here in this particular graph says that where IC becomes 0 such that VC also becomes VCC. This is all explanation we have discussed in the previous slide, right? In the saturation, in the active mode, we say that emitter base junction in a forward bias and collector base junction in the reverse bias. In this particular case, we learned about IC. The collector current becomes 0 such that the voltage across VCE becomes VCC. So while at the top of the load line in the saturation point, see this is a saturation point. So here what happens is the collector current becomes the saturation collector current. IC is equal to, that means maximum current is flowing at this particular point with respect to the collector current. So IC is equals to IC sat. And also VC, then what about the voltage? The voltage becomes VC is equals to VCE saturation. The maximum current flow is observed at this particular point. So when there is a maximum current, obviously there would be a the voltage across the collector and emitter would goes saturated. Then for the BJT to operate in active mode, the condition for BE forward while the BC reverse, this we know. So in the active mode region, there are two modes. In the emitter base junction, it acts as a forward bias. In the collector base junction, it acts as a reverse bias. So in this region, IC is constant for a given value of IB. So for given value of IB, see this is a given value of IB. For IB is equals to 0, IB is equals to 1, IB is equals to 4, IB is equals to 8. So for given value of IB, what happens is IC becomes saturated, that is constant. So but as we see that VCE, when you increase the VCE, what happens? The collector current also increases. The voltage across the collector increases. The current across the collector also increases. Since the BC depletion region, what happens is it widens. So this is the BC depletion region. What happens when you are increasing the collector current and the voltage at the collector and current at the collector? Okay. Voltage at the collector and current at the collector, we see that when you both are increasing, there is a wide depletion region becomes widens. It widens. Then when BJT operates in active region, ideally its output is a linear production of its input signal. So it's a linear production. We see there is a linearity with respect to current and as well as the voltage with respect to collector. So this is all about the operation in active mode, and so here are the textbook references and web references and e-textbooks as well where I have referred. So I encourage you to also refer the same books to get the knowledge, and I hope you understand today's class. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.